Alright, let's dive right into this explainer. Today we're exploring the theoretical building blocks of computer logic, pattern matching, and state machines. You know, if you've ever used a find shortcut in a massive document, or if you've wondered how a website instantly knows your new password doesn't have a special character. Well, you've interacted with exactly what we're talking about today. We are going to break down how computers actually understand rules, and, maybe even more interestingly, where those rules completely fall apart.
So here's our four-step roadmap for this. First, building regular expressions. Second, the DFA machine. Third, the power of closure. And finally, step 4, breaking the system. Let's get to it. Starting with Section 1, building regex, or the rules of the language. To keep things super clean and easy to visualize today, we're going to look at how we actually build these theoretical languages using a really simple alphabet consisting of only 2 letters, A and B. Okay, so what exactly is a regular expression? Essentially, it's a completely rigid rulebook. It dictates exactly what combinations of characters are allowed to exist within a specific language. Honestly, think of it like a very strict bouncer at the door of a club. If the incoming data doesn't perfectly match the precise pattern written on that bouncer's clipboard, it simply doesn't get in. 0 exceptions. And this level of absolute rigidity is exactly what allows computer systems to parse massive amounts of text with incredible speed and accuracy. Let's actually see how this rulebook works in practice. Take a look at this specific rule. It says we can have 0 or more A's, followed by a grouped sequence of 1 B and 0 or more A's repeated. So, given that incredibly strict parameter, does the exact string ABA get past our bouncer? Now, it might seem a bit tricky at first glance, but if we just break it down sequentially, the underlying logic is incredibly straightforward. It absolutely does. That's because those little asterisks, which are known as the clean star, give us the ultimate flexibility of 0 or more repetitions. We can construct A-Bay perfectly just by pulling 1A from that first part and then grabbing 1B followed by 1A from our group section. The rules are strict for sure, but they offer very distinct, reliable pathways to success. You just have to know how to navigate the specific allowances the programmer built right into the pattern.
Now, what if these rules aren't presented as a linear string, but as a grammar? Notice how we're toggling between a starting state S and a secondary state A using our letters. And that little epsilon symbol? That simply represents an empty string. It's essentially the stop sign where our sequence is allowed to successfully terminate. Take just a second to trace how these states feed into each other and think about what kind of pattern this actually creates.
Right, so if you track those transitions carefully, the underlying logic is brilliantly simple. An A does absolutely nothing to change your state. It just loops you right back to where you already are. But a B, that forces you to jump across the aisle between states S and A. Because you start in S and eventually need to finish the string back at a valid stop sign, the only way to successfully terminate is to flip an even number of times. Therefore, your string literally must have an even number of B's.
Now that we know how to write the grammar, let's move right into Section 2, the DFA machine, processing the rules. We've established the parameters, so let's look at the actual computing machinery that reads what we just wrote. Enter the DFA, or Deterministic Finite Automata. This is a theoretical machine that meticulously reads a string from left to right, one single character at a time. It moves through predefined states to figure out if it should accept or reject the input. And the absolute key word here is deterministic. There is no guessing. There is 0 randomness. Every single path is completely locked in from the start, making it an incredibly reliable engine for pattern matching. So here is an interesting puzzle for you to think about. If your machine needs a specific number of states, let's just call it N states, to accept a language, how incredibly complex does a brand new machine need to be to accept everything that language rejects? Basically, its exact opposite. You might intuitively think an inverse operation would require a completely different, much more convoluted setup, right? Well, actually, the mathematical answer is highly elegant. It requires at most N states. You don't need a bigger or more complicated machine at all. All you have to do is take the exact same map of the original machine and simply swap the accepting and non-accepting statuses of the states. It's a perfect inversion, requiring absolutely 0 extra computing overhead. The pure simplicity of this flip is honestly one of the most beautiful aspects of theoretical computer science. But let's complicate things a bit. What if we need to process a string that must simultaneously satisfy 2 completely different, conflicting regular expressions? Say Rule 1 and Rule 2 at the exact same time. We are essentially looking for the intersection of those 2 languages, which requires our machine to perfectly balance 2 distinct sets of strict criteria without failing either one.
Now, you can't just smash the textual expressions together and hope for the best. To find this intersection, you have to build a machine for the first rule, then build a separate machine for the second rule, and finally merge them together mathematically using a super cool technique called product construction. Conceptually, it's basically like running both machines in parallel, side by side, ensuring the new DFA tracks the valid states of both original machines at the exact same time.
And this ability to seamlessly merge machines leads us perfectly into Section 3, the power of closure, combining languages. Let's see how these theoretical building blocks actually protect themselves from breaking, no matter how many times you combine or alter them.
In computer science, regular languages possess what's known as a closure property. Think of it like adding two integers together. You are guaranteed to get another integer, right? Similarly, you can take these languages and perform operations on them. You can combine them with a union, find their intersection, complement them, link them together via concatenation, loop them with a clean star, or even reverse them completely. The output will always miraculously stay within the same family.
This brilliantly illustrates an incredibly robust ecosystem. Performing literally all of the above operations works flawlessly every single time. Every modification just produces a new, perfectly functional regular language. The system never breaks down into something a finite machine can't read, well, as long as you stick to these specific operations. You can twist and fold these rules almost infinitely without ever crashing the underlying theoretical architecture.
However, to truly understand these machines, we have to find out what happens when they actually fail. And that brings us to our final act, exploring where these capabilities hit a hard brick wall in Section 4, breaking the system, theoretical limits.
Let's test these boundaries right now. Imagine a race between two machines. One is looking for a simple substring, ab. The other is trying to identify palindromes, strings that read the exact same forwards and backwards, like the word race car. Which of these tasks completely breaks the system and is not a regular language? The answer reveals a really fundamental limitation of how our computers process information at the most basic level.
The absolute crucial point here is memory. While a DFA can easily remember the last 3 characters to spot AB by moving through a few finite states, it completely and utterly fails at palindromes. Why? Because a DFA essentially has the memory of a goldfish. It completely lacks the massive, dynamic storage required to remember the entire first half of an infinitely long string just so it can check it in reverse. A finite machine simply cannot store infinite historical context. It's just not built for it.
Let's look at one more fatal flaw. What if we ask the machine to verify a string that has an unknown number of A's, followed immediately by the exact same number of B's? Say 50 A's, then exactly 50 B's. Is this mathematical language regular? Can we build a simple finite state machine to guarantee that the two halves of our data are perfectly balanced, no matter how large the numbers get?
This statement is definitively false. Guaranteeing an equal, undefined number of A's and B's requires a machine to essentially tally up the A's as it goes. And because that number could be literally anything, it means the machine needs to be able to count up to infinity. And a finite automaton simply cannot count. It has no internal scratchpad or abacus to hold that tally. Its finite nature makes tracking unbounded growing numbers completely impossible.
Understanding these hard limitations is just as vital as knowing the rules we started with, which leaves us with a perfect mystery to ponder at the end of our explainer today. If regular languages and DFAs can't read a palindrome, and they don't even possess the memory to count to infinity, what kind of theoretical machine actually can? What incredible architecture does a computer need to finally break past the limits of a goldfish's memory?